that's my title. We're going to be focusing on ODZs in this talk. We have a little a team on that too, and some of the folks on this list of contributors are in the audience. You've already been introduced to them. A name that's been left off is Alex Petrie, who is a research faculty member in our department, who made contributions if I get to the end of the talk, but I still have time. And the two individuals here, Craig and Eric, did a lot of the technical work. Eric with regard to the oxygen applications I'm going to talk about, Craig with regard to the GTD N2 gas. And if you really have detailed technical questions about that, I will try to answer, but they're the ones who are going to really know. Okay, so our emphasis, first, everybody can hear me in the room? I'm projecting okay? Okay, great. Okay. The emphasis here is on low oxygen regions. We've already been some mention of it, but from my perspective as a nitrogen guy, this is where a lot of interesting stuff is happening regarding, is it going by itself?
It's going by itself, but I couldn't find the animation.
Okay, this is going to be a problem. I better speak faster. Anyway, or click faster. But basically, because we have an idea of where they are, oxygen gets very low, practically anoxic, even though sulfide doesn't build up. And anoxic to the point that it turns on other microbial processes, including denitrification and anammox. And as a result, there's a lot of conversion of fixed nitrogen to N2 gas. One of the big reasons we're interested in this, to understand what's forcing that ultimately and what's the impact of that in terms of climate change. Also, it's an important source of trace greenhouse gases like nitrous oxide, Annie and Colette's study, amongst others. And obviously, when you're living around these regions, whether or not there's penetration of low oxygen waters, that's going to affect fisheries and such. In terms of what we want to measure from floats, that's a little unique from the rest of the BGC Argo program, the GO-BGC Argo program. You're hearing about is that we really have an interest in nanomolar of oxygen. And you would think, well, that's sort of in the weeds, but why do we care about, in these regions, students of microbiology, why do we care about nanomolar oxygen? Anybody catch that in your nitrogen cycling class or marine microbiology class? Why do we want to measure so low, like get down to like below 1 micromolar?
The science has changed.
You know it. I'm asking them.
Oh.
I know you know.
Because of the enzyme that bend the oxygen can do so at very, very low oxygen concentration.
And as a consequence, so that is what turns on these other processes like nitrate, dissimilatory nitrate reduction, and anammox, so on and so forth. So that's why we care about being able to measure so low in these particular regions. We also like to look at the buildup of the products of these processes. So by being able to measure the small amount of biogenic nitrogen on the order of maybe at most 20 or 30 micromolar on top of 400 micromolar, that's a technical challenge, especially doing it from a float. On the other hand, we want to look at the complement, what's the removal of nitrogen. And there are, whereas we cannot measure phosphate yet from floats, look at novel ways of using the nitrate results from sensors that can invent it, and others. That's rather promising. These first two I'm going to be focusing on in the talk. Ken also gave a little tease on the nitrite, and I was trying to tease him why we care about nitrite, but we do a lot. I've been asking for, how many years I've been asking about the measure? A lot? A few. So, and Mari solved it actually.
Wait no more.
Yes, so I'll talk to her from now on in that regard. Anyway, I better move on. So, oops. And so we had a couple cruises to deploy novel floats that on a project that Eric and Craig and I are PIs on. And the last and longest cruise was on the Sally Ride, and we did this in the last phase of the pandemic, so it was a bit of a challenge. So we did take our isolation in Costa Rica and pick our lemon and made it into lemonade. I won't tell you anything more about that, but we left Costa Rica and did this on zigzag up to San Diego. But part of it was using the availability in real time of satellites from the Ocean Virtual Laboratory with great data products online to see where chlorophyll and the eddies and all that were, and drive the ship through the eddies. So we hit 1, 2, 3 eddies. We really focused on these two big eddies, and we had our own floats we we dropped into the ocean. We obviously did a lot of CT work in collecting data to help us understand the floats in the process of carrying out this track. And also we were deploying floats for Argo O2 as well as for GO-BGC. And our group will be working on the data from the GO-BGC. 4 floats, right? Well, there were 4 floats we deployed. I think 3 did well, but maybe we dropped one. Anyway, say no more. And of the floats that are as part of our specialized project, which we're going to call ODZ floats, these were their tracks and you can see the ones that survived the longest because they were dropped specifically in the eddies and had a parking depth shallower than was standard for GO-BGC, around 200 meters. Well, we're not going to call them parking depths. You can see in a moment that we want to do science at what we call these drift depths. That they followed, they moved along with the eddy. So this is sort of the other way of approaching the science, is that if you want to study a particular phenomenon, you put your floats there and you gather the data at the resolution you need. That's the dissonance with the creative dissonance compared to the approach that Ken was just describing. Also, we wanted to have unique missions that we were testing out to see if we could appropriate for our scientific objectives, which, might have had faster, where basically the float would do, step profiles. Because part of the reason we need these step profiles is because one of the sensors, the GTD, which measures the nitrogen, has a relatively long response time in the order of 15 minutes or so, and that actually depends on, if you're not pumping which uses up water, uses up not water, energy from the battery, that if you're not pumping water over the surface of the GTD's membrane, that increases its response time. So we need to get profiles. We had to have the float actually stop a little bit along the way so we can get equilibrated values for nitrogen gas pressure. And then we were trying out to see if we collected data at depths of interest where we think there was a lot of biogeochemical activity, where we can measure changes over time as the float is ideally undergoing a Lagrangian drift, so that all the mixing and vector terms would sort of go away in our conservation equation, and the change over time in our scalar actually represents a biogeochemical rate. So that's what we're testing out here. And then and these floats would have a GTD, which is a gas tension device, which measures dissolved gas pressure, which we convert hopefully into biogenic nitrogen, and their altodes, which we both have one stuck into the water, but also one that represents a 0 reference in a sulfide solution. And it's Eric who worked on all the details of trying to squeeze as much resolution and accuracy out of that approach. And this was that before was the idealized mission. This was an actual mission from one of the floats, where in the first part of this time, Eric is trying to figure out how to control the float. Yes, it was a little, because one of the problems was that the facility was lower than my experts anticipated. So the buoyancy aspects of getting the float up and down was a little more complicated than they anticipate from standard density profiles in the rest of the ocean. The salinity up here was like approaching 33, where down, right here was around 35. So that had a big influence on buoyancy and density. But you can see finally in the last bits of the lifetime of this float, we're able to do these drifts. And the interesting thing is that now if we focus on that, those drifts, you see an interesting phenomenon, which is maybe another lemon that we can make into lemonade if we think hard about it. Get the right button here. There we go. That these are the actual drifts with the expanded depth scale. So now this is about 10 meters here. So clearly they're not sticking exactly to the constant depth. That's something we have to see if that's how important that is in terms of our original goals. But you see there's all these wiggles. It's not noise. So those of you who have a quick way of analyzing data with your eyeballs, what do you think the signal is? Or yes, it's kind of internal wave, or internal tides, because this is 10 days. I get a trick. I didn't give you a chance to realize that these are 10-day drifts. So what's happening is that some sort of internal motion is happening. In this case, sort of semi-diurnal. And you would think, oh, the float goes, but the float doesn't exactly follow it. So it's actually, if I did this with density, it would also show an oscillation density because the float is not quite keeping up. So we haven't pursued it, but it's actually doing micro profiling along each of these drifts. So we can, hopefully we can dig in and we can actually, if the data resolution is good enough, we can actually see if there's changes in the gradient, vertical gradient, over a 10-day period. That would be an interesting, not unexpected experiment we could do. Okay, going on. Okay, so there's a bunch of complicated equations here, and how do you take what the GTD measures in terms of total dissolved gas pressure and we turn it into a biogenic nitrogen signal? It's a little more complicated than we anticipated, partly because there is a physical background of excess nitrogen that we haven't quite anticipated. It has to do with basically bubble injection of water mass sources and mixing and things like that. So all those who took chemical oceanography would start thinking, oh, yeah, how do you change apparent gas solubility? Okay, that have these exceptions from non-ideality. Well, that's what we actually have to go figure out in the system to understand the background signal so that we can tease out this. So we actually have a paper that goes through how our first attempt at how we're doing that appeared in, was it the volume of Frontiers in Marine Science? And he's one of the editors. I'm sure some of you others have hopefully seen it. I've seen the volume. And then this is the result of a comparison, sort of, nope. Go back, okay. That basically calculate biogenic nitrogen from the same region within the ODZ of the Eastern Tropical North Pacific, where we have this maximum at about 200, 300 meters depth, obviously lower at depth outside the ODZ. We have funny business going on with the gases toward the surface. It's not understandably in terms of what this line represents, but generally we've calculated several different ways. One from typical nutrient ways of looking at the nitrate versus phosphate relation. That's the nuts parts, and those are in the little X's and dots. Then we have a GTD mounted on the ship's CTD, okay, and that's represented by the bigger circles and some of the green circles here. And then the important point here is then we have a GTD on a float that was deployed nearby that gets us pretty close. So we're at a point where we think we're close to being able to figure out biogenic nitrogen produced by denitrification from a float. And that's one of the big things that where we're at with this project. Clearly a little more work to be done, but I think we're on a good track there. And the other thing I wanted to look at was, okay, how we're doing with our original goal of trying to look at the rate of denitrification from the GTD during a drift. Now, what I've done here is I've not converted the GTD pressure to biogenic nitrogen at this point yet. But basically, and the only thing that should be influencing the pressure along a drift is denitrification in principle. So you would say, oh, and that is on the scale of millibars. So basically, each of these major gradients would represent about maybe 1 micromole of nitrogen gas, each of one of these major units here. So you could get a sense of that we're down to be able to look at very small changes over time, and over a 10-day period, we should be able to resolve rates of denitrification, or I should say N2 production, of about 0.1 nanomoles per day, something like that. It's getting really down in the weeds. But also, but the story's not yet so simple. You can say, wow, look at this. Look, we're seeing these rates of increase in N2 gas. That should be our rate of production. However, if you recall, the float was slowly sinking. And what we're really seeing here is not net denitrification, but just the float slowly descending in water with a higher nitrogen gas pressure. So we're not quite there yet, but we're getting real close. Uh-oh. Uh-oh. I'm close. Okay, so we're also figuring out how to do oxygen real low. Okay, this is from what Eric's doing. So this is oxygen from that same float. And again, if looking at the oxygen and the drifts, you can see we're here down at looking at differences on the order of maybe 15 nanomole oxygens, plus or minus. So, and the important thing that we are seeing from this cruise, and this is from a different float, that's on the other side of the same eddy, is that we see these interesting oxygen intrusions, which have been mentioned in some papers. And that, I guess, where I will end is that one of the things that we're tying it all together, and is that when we look at the eddy fields from satellites in this case, and combine it with the float data, we can get an idea of from backtracking using analysis that Alice did of where some mesoscale filaments are present. And this is where I'll get to the last slide here. Skip this one, do a chem there. That we can do backtracking, and we see that the presence of these oxygen intrusions appear to be coming from where the eddies are generated near the coast. And that our hypothesis is that even though this whole region in here is low in oxygen, that a coastal current that is being combined with the eddies as they form is introducing filaments of low level of oxygen right into the heart of the ODZ. And again, from those of you who are more interested in the microbiology of this, that actually is going to have a big impact on the kinds of processes that we see. And like a lot of things that we are finding out in oceanography, it's the events, the things that are happening when you're not necessarily there on the ship, which are making a big difference to the net effect of what you see. So, again, I had too much in my talk, but I hope you got something out of it. Thank you. Go ahead, please.
So I'm just wondering, so you can see these little oxygen intrusions, and you've got these floats that are in the eddies. Can you combine that with Murray's nitrite data to comment at all on like anoxic nitrite oxidation that might actually be fueled by, nitrite oxidation that's happening in waters that we think of as being anoxic, but is potentially fueled by these kinds of oxygen
that's,
eddies?
I mean, a lot of people say that's a great question, but that is really a great question. And I think that it gets to, if you don't mind, I'm going to just give a little background. The onset, a major surprise in the last, I would say 10 years, at least 10 years, in the whole field of understanding nitrogen cycling low oxygen environments was the realization that a large percentage of the nitrate that was in the first stage of denitrification reduced to nitrite actually goes back to nitrate. Even though there doesn't appear to be any available oxygen, at least thought that oxygen is what you need to do nitrite oxidation in most of the ocean, and here it appears to be happening in the absence. And that gets exactly to the point that maybe that's happening sporadically when there are these oxygen intrusions. And in fact, that's why I think, I'd like to see future work where the kinds of incubation experiments that our colleagues are doing would take advantage that when we know these things are there, to see what those processes are. But yeah, I think now that we have the ability to, hopefully we have the ability, we do have the ability to look at nitrite from floats, we can then see the correlation between these events and the other things that are happening. Oh, come on, stand up and be proud. Okay, thank you.
Dan is the one. Yeah, so the three floats that we have, the one on the north is my favorite one because there is no oxygen intrusion, so it's easy to process. And then the two ones on the south have a lot of oxygen intrusion. In fact, all year long, it's almost never zero. Always comes up. Yeah, it's gonna be challenging one. Kind of breaks the code. So I'm still not 100% confident about the ones on the south, but the one on the north is good.
Listen, just because something conforms to your expectations doesn't mean it's a good one. But I think the other interesting thing is that one thing I didn't have a chance to point out is that the one that was the good one is on one side of an eddy, and this is on the other side. Okay, what's that? Okay. Am I out of time?
One quick question. Sorry.
So, in terms of like this discussion, the anomalous events versus like the statistical event, right? We know they're both happening. One uses both essentially. When you're deploying those floats, is it all possible to do some extended command? I'm leaving this float here. Where I get the background every 10 days. Oh, I look at the satellite, I see there's a hurricane, I see there's a pool, eddy going to, and now I want to see a day, I want to control sizes. Is that something you're able to do in these deployments, or are you guys like setting the firmware on the ship, putting it back in?
Probably the folks who actually have been driving floats for a long time can answer it, but my knowledge of it is that since the communication with the satellite is two-way, that if these floats are not part of the GO-BGC program, then the owner operator can do that. Okay, and that actually would be an alternative, like I would say, the complementary way of running float experiments. In this case, they're experiments. Okay.
As I can address, like, this definitely can. There are certain mission parameters that you can change, and this is another, potential compromise solution that people have proposed in the past. But each time you change, so like, let's say if a flow just in between flying islands, we have to change it in the depth, part depth, so it doesn't hit the bottom. Like, yes, we do that when needed, but we also, so when each time you do that, it's power, right? And then and it still compromises the longevity of the mission, right? And so you're still letting into the ability to create these arrays in a sustained fashion, And then so maybe perhaps one day we'll get there, but like right now we have not done that. There's no formal way to do that in like, competitive and proposal kind of situation, right? And then so right now we but again, these floats, if you want to purchase them for your process studies, then you can absolutely do that. They are powerful.
First, you have to get your reviewers to accept. I will say that our first, I'm sorry, Ken, just a second, if I can make a quick comment. Our first attempts to do this kind of work where the actual target was to study eddies off Peru. As an outcome of work Annie and I did, showing some of these eddies really sucked all the nitrate away. And there was one reviewer who just said, I don't think the eddies are important, and I don't think you're going to be able to find them when you need them and put the floats in there, and they won't stay in the eddies. Well, maybe now we can say, no, maybe that reviewer was not quite right.
Actually, we have I'll do it real quick. So there's some precedent, like in the Argo core program. There's additional funding that comes in, like when hurricanes come on, when we can upcycle certain core floats, but it's kind of the thing where we need to reach a sustained global observatory and then think about how we work together to find resources. I was just going to say, so our proposal is to build a sustained global array, and every time you do something like change cycle times, as you said, it impact lifetimes. So we've had a vociferous discussion on the executive team doing this, and so we feel conflicted because these are not our floats, they're your floats. But the proposal was funded to build a stable array. So I said, hey, hurricane coming over this float, quick, let's change the cycle time to once a day, and we'll see the hurricane. And the executive committee said, no, that would be sort of internal conflict of interest for us to change the science mission of the array that we got funded for to something to personally benefit ourselves. And personally? Well, I can write a paper. I would be the one who knew about the cycle changes. And so we are trying to be totally above board about how this all happens, but so if you feel strongly about this, there's an external advisory committee headed by Dennis Hansel that provides advice to us, and fact is, we are running this for the community, not for Ken Johnson, not for Yui Takeshita. And, so it's not really, would be unfair for us to kind of try and do our own specialized science with something that if you came and asked me, I'd tell you to go jump in the lake, Mark.
But that is a conflict, right? And so there's different science that can be enabled by profiling faster and then by sustaining a longer array. And then so we are not in the position to make the call of which one is better, which one is worth sacrificing the battery rate and stuff. And so if there was a formalized competitive process to NSF, reviewers, whatever, that would probably be the most appropriate way to do that. But right now,
and that's exactly the model we talk about
this
at Seattle, and this is the model we pursued.
But it is, sort of the final discussion was when we get the array built and it's 500 sustained, and if there's extra energy, that could be made available to the community. But right now, we promised to build a 500 float array, And, and we haven't finished that yet, so we shouldn't be giving away parts of the array until we finish what we were funded to do.
And remember, like, core Argo, this is the last,
If
core Argo is.
I can say
Yeah,
one
sure.
thing.
Core
actually.
Argo is the funding is flat or even going down, so the bill, we kind of think, at least I have thought that, Argo's fine. Like, it is sustained, it's an established project. We're still, like, struggling with funding, and the array size is, is shrinking. And then so like this fundamental one of the most important projects in arrays of oceanography is already a compromise. And BGC Argo, they're SOCOM, and the BGC is contributing all of those missing profiles to the core Argo array, right? And then so this science discussion goes beyond BGC, it goes to core Argo, like this fundamental knowledge of how much the ocean is heating, right? Because if we don't know that, we are completely screwed with climate change. We can't make any sort of predictions. So anyway, so it is kind of like an onion, right? The more you peel, you're like, oh crap, but that is the reality, but like we do want, but this is why these discussions are so important. And it is a very, very complicated.
So if I were to add to this, I say, I'm ecstatic. I was ecstatic when your project got funded. And I certainly know, even if I never did this again, I would, if I pursued it in science, I would benefit as well as all of you. At the same time, if I want to continue, I think, okay, how can your experience, I understand, you cannot say, I'm not going to ask you, say, oh, can you take one of your floats and do that with my science? You're not set up to do that. But at the same time, when I go do my proposal, or I try to, to talk to Betty about saying, oh, I have this opportunity to build ODZ floats, that from your experience dealing with the float manufacturer, with the sensors, how can, I be more economical? How can you both in time and all money based on your experience? And I think there are points of leverage that we could talk about.
We'd be glad to talk to you about
Okay.
that.
And there is precedence for like data, like us, like partners, trust in the data for, so your whole life doesn't have to spend that up. But for example, so there are opportunities. Okay.